This is sample 10-2 from page 452, where we are going to calculate the kinetic energy of a wind turbine. So we're told that the blades of the wind turbine have a combined rotational inertia of 2,000 kilogram meters squared for rotation around the turbine axis. If the blades make 4 complete revolutions every minute, what is the rotational kinetic energy of the blade? So in these early stages where we don't really know how to calculate rotational inertia, they can just give it to us and we can write it down and use it, no problem. And by the end of the day, you'll know how to calculate it for certain objects. So we've got that right there. The other piece of information we're told is that the blades make 4 complete revolutions every minute. So we're talking about angular frequency or angular speed here. However, we're going to have to do some converting because they say it's 4 revolutions per minute. Remember, revolutions per minute is also often, abbreviated RPM. So if you see that, make sure you know what that means. So we can't use this in our formula. We've got to use radians per second if we want to come up with energy in joules, which we do. So a quick unit conversion here, a minute is 60 seconds, and a revolution is 2 pi rads, gives us an angular speed of 0.419 rads per second. Now again, back when we talked about rotational kinematics, if everything's in revolutions per minute and alpha is in revolutions per minute squared, you can keep that concept for angular speed. But if you're going to calculate energy, you cannot. You must have radians per second. So make sure, I know that was in the slideshow, make sure it's in your notes. So now I have I and omega, so a quick check of my formula tells me that the kinetic energy of a rotating object is 1/2 I omega squared. So let's do our plug and chug here, and let's make sure we get joules, okay? Because we haven't done this before. So if our rotational inertia is 2,000 kilograms and meter square, all upstairs, okay? And our omega is 0.419 rads per second. And this quantity is squared, but since we're trying to keep track of units here, I'm just going to write it twice so that we can see what happens. Okay, the numbers, half times 2,000 times 0.419 squared, that's not very interesting. It gives us 176. Fine. So what kind of units do we have here? We have kilogram meters squared per second squared times radians squared. So kilogram, I'm going to write meters twice, and you'll see why in a moment. I'm going to put my second squared here, and I'm going to put my radians squared here. Now, what I want you to realize is that this here, a kilogram meter per second squared, is a Newton, and a Newton meter is a joule. Okay, then what about this? Well, remember, radian is just a unit of convenience. It's a unit to put in there because, remember, a radian is a ratio of lengths, and the unit cancels out. So what we can do with radians is what we can do with no other units in the entire curriculum, and that is take them out when we don't need them and plop them in when we do. So we are going to do the first of those things and get rid of them. And so my kilogram meter second squared times a meter gives me 176 joules. Now, you don't have to have that exhaustive conversation every time you calculate this, but I want to show you that even with this kind of weird new unit called rotational inertia, we still get energy in joules. That's one of the big constants in physics. If you're talking about energy, the unit is in joules. So that's our first sample, and on to the next one.